Hello everyone, and welcome to the beginning of the course on digital systems design, which is a follow-up to the course on digital systems that you should have already completed by now. This course, as the title suggests, goes a little bit deeper into the process of how we would actually design reasonably large digital systems, right? And of course there are a lot of limitations in terms of the scope of what the course can cover, which hopefully will become clear as we move forward through the course. One of the things that we will be doing extensively throughout the course is the use of hardware description languages in order to actually implement certain kinds of digital systems, and in the process also go through the steps of simulating these designs and, where possible, to try and actually implement them on hardware. So let's start the course with a recap of the digital systems course, right? Everything that I mentioned in this portion is something that you are expected to already know before you get into this course on digital systems design. In other words, when I say digital systems, I'm talking to the introductory digital systems course, and the concepts that I will be covering in this recap over here are essentially things that would have been covered in that course to various degrees of detail. If some of these parts over here are not entirely clear to you, I would strongly suggest going back and revising those before you go further with the present course. Alright, so a number of different concepts that you would have come across in the course on the introduction to digital systems. The very first and foremost is the idea of Boolean logic, right? And Boolean logic essentially deals with the concept of reasoning, right? The entire thing owes its origins to a book written by George Boole in the 19th century, and the title of the book was The Laws of Thought. The whole idea over there was, can we take sentences, normal English sentences that we speak, and convert them into logical statements, and how do we combine those statements together in such a way that we can construct more complex statements, or how do we infer the truth values of different statements? Which means that since we are talking about truth values, we have two fundamental quantities, true and false, which we also call as logic values. These are the sort of primitive building blocks of the whole idea of how we reason with logic. For example, we can take a statement and say the sun is hot, and based on our experience we know that that statement is true. On the other hand, if I say the sun is cold, equally well I can also say that based on our experience that statement is false. Now of course there are a lot more subtleties over there, because then comes the question of how do you define hot, how do you define cold, cold or hot in what sense. For example, the sun is probably colder than certain other stars that exist. That's not what we are getting into. We are talking about sentences or propositions, as they are called, that you can assign a truth value to, and the whole idea of Boolean logic was how do we combine these together. Now in the process, a number of operations were defined, the most well known of them being the AND operation, OR and NOT. So NOT is basically an inversion. One way of looking at it would be this, to say the sun is not cold, which basically says I am taking a proposition, the sun is cold, and I am inverting it, right? I am changing the nature of the proposition. I could also try and combine different propositions together, right, and sort of construct more complicated sentences. For example, if I have a sentence which says I will succeed in digital design if and only if I understand AND gates or I am really good at guessing, right? Now these things that I have highlighted in blue, the OR is of course well known over here, right? It basically says either one of these statements should be true, in which case this entire thing that I have put within brackets over here is true. The AND gate that I mentioned here is actually a bit of a red herring. It has nothing to do with the actual logical value of this particular sentence. Now this if and only if is also a type of logical operation. It basically says only if both of these are true or if both of these are false, right? Both of them essentially result in the same final output, right? So intuitively we know how to sort of go through and understand or analyze these kinds of statements. What Boolean logic did was to formalize that process. And in the 20th century, as a result of work on switching theory by Claude Shannon, this entire thing was applied in the context of actually understanding digital electronic circuits. in some sense it gave birth to the whole area of digital switching theory, and ultimately results in pretty much every kind of computing system or digital computing system that we are pretty much surrounded by these days. Now, that was the theory. From there we move on to the idea of gates, and here we once again have a number of different terms that we use. One of them is the idea of a gate such as an AND gate. This is the typical symbol that's used for that. What we mean over here is there is a gate. By the shape of the gate we know that this is an AND gate. It has two inputs, x and y, which are basically named variables, so to speak, and it has one output, z, which is defined as x ampersand y or x and y or and of x comma y. These are all different notations that you would come across depending on the way that you are using in order to represent the expression. And what it means is that the output of this z is true only if x is equal to true and y is equal to true. In other words, if both of these inputs are true, then the output is also considered to be true, right? Now, so far we are talking in terms of truth values. As I said, Boolean logic deals with reasoning, it deals with the truth of propositions, and it's all about how you can connect such statements together logically. On the other hand, when we got to switching theory, there was this requirement to also translate that into something physical, a physical quantity. Truth and falsity are not physical quantities, but much closer is if we can sort of interpret these as numbers, ones and zeros, right? And a sort of natural alternative notation that sort of came up along the way was to say, why don't we consider a truth value to be the value 1 and the false value to be the value 0. Now, keep in mind that this is a convention. It's something that we are basically adopting and saying, okay, 1 will be considered as true, 0 will be considered as false, and based on that I can now perform a new set of operations and connect them with how the truth operations work. Now, even further, when we actually got to the point of building circuits that actually have this kind of behavior, then step that was taken was we go from truth and say it is equivalent to the value 1, and we further say this actually corresponds to a high logical state, and the reason for that was it typically corresponded to a particular voltage somewhere in a circuit corresponding to a value of the supply voltage. Similarly, f would be 0 or a logic low because it would correspond to a ground. This is actually a very important thing to keep in mind. These are pure conventions. There is nothing fundamental that says that a 1 or a true value needs to be a VDD or logic high. Just because you see VDD in a circuit does not automatically imply that it is a true value, or just because you see ground somewhere does not automatically imply that it is a false value, right? These are conventions. In most cases that we know of, in most circuit families that we know of or that have been built, that convention holds true. But there are cases where it is not. So for example, there are current mode logic where, for example, the presence or absence of current or a high current and a low current would indicate different values in terms of whether a particular value is seen as true or false. So these conventions that true is 1, false is 0, it's logic high, logic low and so on are conventions. You need to keep that in mind. For most of this course at least, that convention holds true. We don't normally need to sort of consider that there might be exceptions to this scenario, but it is something to keep at the back of your mind while you go through and study digital logic. Okay, so now we have the concept of a gate. We can now think of a way by which we can actually create a way of understanding what the input to output relationships of that gate are. And in some sense, the most general way of doing that is what's called a truth table. Now, what's a truth table? It basically says there are two inputs, x and y, and if I assume that the inputs are either 0 or 1, I'm going to just use zeros and ones from now onwards instead of true and false, because zeros and ones also apply in a different context as we will get to later, right? What you can see is that for this particular gate, there are 4 possible different input combinations. X and y are both 0, x is 0, y is 1, x is 1, y is 0, or x and y are both 1. Now these are the only 4 possible input combinations. The AND gate is a very special version of this particular truth table where we say that the z value corresponds to these outputs. That is, when the inputs are 0, 0, the output is 0. If it's 0, 1, the output is 0. If it's 1, 0, the output is 0. And if the inputs are 1, 1, the output becomes 1. In other words, only when both the inputs are 1, the output of this gate becomes 1. This truth table and this gate are equivalent. We use them interchangeably. We also use the expression x ampersand y or and of x comma y. All of them basically refer to the same computation. Right? Now, the interesting thing is this is a pure mathematical construct. It does not care about how you implement it. It does not care about the existence of transistors or otherwise. Right? All it says is you want to do some kind of a computation. It has so many inputs. These are what the outputs should be. And as we will see later, this is actually a very interesting, it's put to an interesting use in a special kind of circuit called an FPGA that we will come across later. Now, one small side note over here, instead of 2 inputs over here, if we had 3 inputs, let's say, then the number of combinations would be 0, 0, 0, 0, 0, 1, 0, 1, 0 and so on. In other words, there would be 2 power 3 combinations. Right? If there were 4 inputs, x, y, z and t, right, there would be 2 power 4 possible combinations. Now, for each of those combinations, the output could be either a 0 or a 1. And for each combinations of zeros and ones that you have over here, it basically represents one particular function, right, one input to output mapping. From that, you can sort of infer that if I have n inputs, I have 2 to the power of n combinations and therefore 2 to the power of 2 to the power of n possible functions, right. For 2 inputs, that basically means it's 2 to the power of 4 or 16 possible functions, right, because I could have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0 and so on, all the possible different functions that I have out there. Very few of them actually have names associated with them, as you probably know, right. The AND, OR, the NOT is not exactly a 2 input gate, but there are XOR, XNOR. That's about it, right. Those are the ones that we know of, right. There are names given for a few others, but in general not all the 2 power 4 different functions have names associated with them, but they do exist and it is possible to come up with an equation where they are actually used. Alright, now continuing on our recap, one of the other things that you would have come across is the notion of Boolean optimization, right. And what we do over there is we say that there are certain laws that these Boolean expressions follow, such as, for example, the famous De Morgan's laws, right, which basically says something like if I have a and an inversion of the and, I can basically invert the inputs and OR them together, right. Similarly, if I have a plus b the whole bar, it is a bar and b bar, right. You can even think of these in terms of logical statements, right, and they actually have like nice intuitive physical meanings, but as far as we are concerned, this is a pure mathematical construct. The interesting thing is by systematically applying these kind of laws, right, and transformations to the expressions, it is possible to modify them. And one particular way of modifying those is the use of so-called Karnaugh maps, right, where what we do is, let's say for example, if I had 3 inputs A, B and C, I can say, for example, since I have ones in 3 locations, that basically corresponds to these 3 terms A, B, C bar, A, B, C and A bar, B, C, right. How do I know that? Because this basically corresponds to 0, 0, 0, 1, 1, 1, 1, 0. So this 1, 1 over here corresponds to A, B, and this 0 over here corresponds to C bar. So the first term that I have is A, B, C bar. What Karnaugh maps recognize is the fact that if I have 2 consecutive ones in adjacent locations, in the way that this is written, they can actually be collapsed into a single term, right. And therefore, by simplifying this, we can actually end up and say that this term actually corresponds to AB plus BC. Can this be further simplified? Yeah, you could probably factor out the B and write it as B and A plus C, but it's essentially the same number of terms that you have in that case as well. So there are optimizations that can be applied. Now in practice, apart from the Introduction to Digital Systems course, it is actually rare to use these. Right. What we will be doing later, at least in this course, we will never actually be using Karnaugh maps in practice. What we will do is to use computer aided design tools that automatically do all of this behind the scenes and give us highly optimized versions of the expressions that we have. So far we have been talking about so-called combinational circuit elements, and the idea of a combinational element is that it has two inputs. If any one of the inputs changes, the output essentially immediately responds, right? Any change in the input could cause a change in the output. It could also cause the output to remain the same, but one thing you can be sure of is it's not going to cause the output to change after some time, right? In contrast, you have the notion of so-called sequential elements. These are used for the purpose of storage. They allow us to control when a particular signal is going to change. The most classic example of that is the so-called D-type flip-flop, right? It has one clock input, and that clock is basically the control signal that determines when the output can change. Okay, what does it do? It basically says if I have a D input, which is the data input, and Q is the term that I use for my output, what I am going to do over here is D can change as much as it wants, but Q will change only under controlled conditions. In other words, every change that I see in Q over here will correspond to a corresponding clock edge, right, on the clock signal. At that point, it will basically go and see what is the value of D and copy that value over to the output. The fact that D underwent a number of transitions in here is completely ignored. It has no way of coming through to the output because all those happen between these two clock edges, and therefore they get ignored, right? In this way, a flip-flop allows you to sort of control when a output or a value is going to change, and this allows us to basically build up more complicated systems that have the notion of evolving with time, because the clock essentially brings in this notion of time and allows us to control when certain things are going to change. Now, there are a couple of terms, in particular flip-flops and registers, that we are going to keep coming across over here, right? The term edge triggered is something that you should be familiar with. It basically refers to the fact that this flip-flop, right, which is essentially a term used for something which basically switches between two states, either 0 or 1, right? This flip-flop can basically change its value only when there is a positive edge on the clock, that is to say when the clock undergoes a transition from 0 to 1. Any other change in the clock or the clock remaining stationary and this input and output are effectively disconnected from each other. There can be no way of propagating data. Okay. So edge triggered flip-flops are the most common type of flip-flop that we will be using throughout this course. You would have come across certain things such as level triggered. They are usually referred to as latches, right? So there would be like RS latches, and latches can in turn be used in order to build flip-flops and so on, right? Now in practice, that's not really how things are done. You do not actually use latches to build up flip-flops. You may, but that is a detail that is actually invisible to the designer most of the time, right? What actually happens in practice is the flip-flops are designed and optimized directly at the transistor level in such a way that you only know about their abstract behavior, and that's all that you really need to care about. Okay. There are also certain other kinds of signals associated with flip-flops, the set reset signals. There are flip-flops known as toggle flip-flops, there are flip-flops known as JK flip-flops. None of that is going to matter as far as this course is concerned, right? We are primarily going to focus just on the edge triggered D-type flip-flop because it can basically capture pretty much any kind of functionality that can be done by any one of the others. What usually ends up happening is, especially if you have level triggered latches, one particular aspect of the design process, which is called timing analysis, becomes significantly harder to do, right? And by restricting ourselves to so-called synchronous designs, where in particular we are going to be working just with positive edge triggered D-type flip-flops, right? You can actually do a significant amount of analysis on circuits, right? And even prove certain properties such as how they will evolve with time. Okay. Now, this is not the only kind of digital circuit. There do exist circuits where we can even use asynchronous logic, you can use latch based design, you can use other kinds of flip-flops than D-type flip-flops. There can be circuits with both positive and negative edge triggers being used. For most parts of this course, we will not be considering any of those different options, right? Because the focus is primarily on synchronous design and positive edge triggered, positive or negative, but we stick to one particular edge throughout the design, right? This is in general not losing generality, right? Most things that can be done by other techniques can be achieved by means of these edge triggered flip-flops, which is why we restrict ourselves to those. It turns out that a lot of the analysis that you can do with these makes it a much more powerful way of designing circuits than if you introduce all the other kinds of complications. One more note over here is that the word register is something that I will be commonly using more or less interchangeably with the term flip-flop, right? There are scenarios where the use of the word register is a bit more nuanced. It actually usually means a multi-bit value that's being stored somewhere, but for all practical purposes a register is something that stores a bit value. A flip-flop is also something that stores a bit value, so in most cases there will be no confusion, right? And in case you see it, you should be able to infer from the context whether or not this is actually a D-type flip-flop or some other kind of register that is a more complex system. Now, so far so good. We were purely talking about Boolean algebra and the idea of how we can construct gates and various kinds of elements that allow us to manipulate these truth values. Now, the interesting thing was at some point we said that these logical values t and f could also be mapped into 1 and 0, and that actually opens up a whole new set of ideas over here, which is that 1 and 0 now remind us of the fact that these are numerical digits, right? Of course, in the decimal system we are used to 0, 1, 2, 3 all the way up to 9. This is only 0 and 1, but we can still think of them as numerical digits, and we can start to think of numbers by assigning place values to these, which means, for example, that I could take a sequence of bits 0, 1, 0, 1 and say, okay, I am now going to interpret this as a number. What kind of number? I am going to assign a place value to it. So just like we have units, tens, hundreds, thousands and so on in the decimal system, here we have the units place, the 2's place, the 2 power 2 place, the 2 power 3 place, right? We don't normally call them the 2's place, the 4's place, the 8's place. You could if you wanted to, because that's precisely what they are. The bottom line is, because we have assigned this interpretation, now I can take this string of bits and say, okay, it actually has the value 1 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 power 2 plus 0 into 2 power 3, which is the number 5 if I was using the decimal number system, right? And the nice part about this is again a convention, an interpretation, right? We could choose a different number system. We could basically say that I have a set of bits and they actually mean something else. But the good part is, if I am sure that I want to basically treat these as some kind of numbers, then this is how I would interpret their values. What's even better is, now that we know that a 1, for example, corresponds to a value of t and a 0 corresponds to a value of f, it turns out that when we start doing operations, like what happens if we add two numbers together, how do we generate a carry output from adding two numbers together, right? How do we combine numbers numerically or with arithmetic in different ways? All of those operations can now be converted into equivalent Boolean operations, which means we can write Boolean expressions, we can simplify them, we can optimize them, and finally we can implement them using gates, right? Now this is actually quite a nice insight if you think about it, right? There is nothing fundamentally obvious that tells you that yes, numbers and truth values are the same, but the moment you sort of recognize that, it opens up a large set of new computations that can be performed by treating numbers as truth values. One last thing that we need to know about how complicated digital systems can be built is the notion of a so-called finite state machine, right? And over here we have this idea of a so-called system, right? A system is defined as something within this box, and what do we have? We have certain inputs, and that system also has certain outputs, and more importantly the system has something called an internal state. Now that state, the moment we use the word state, it is something that basically indicates something that evolves over time, right? So we have already brought in the notion of time, which tells us that presumably that state is something that we are going to be storing in flip-flops or registers, right? Now that's good, because we already know how to build registers, or at least we hope we do, right? And now it's just a question of how do we use these registers in such a way as to actually implement the idea of state, okay? Now when we have state, what we can say is we can also have something which basically describes the evolution of this state, right, as a set of update equations, which basically tells us that I have a present state, I have a certain computation which depends on the present state as well as possibly on the present inputs, right, and is finally going to give us an updated version of the state. It's going to tell us, okay, what new state do I move to? I can also perform some computations and generate outputs based on my present state, and again possibly based on the inputs as well, right. Now, where do we use something like this? We will be using it extensively as we move forward. Primarily what this allows us to do is, for example, to apply sequences of operations. If we want to go through a particular set of operations in sequence, the first thing we will try and recognize is, okay, how do I enable an operation? Possibly by giving one particular signal to a set of logic gates. Now, how do I make sure that that enabling signal comes at the right place at the right time? I can have a state machine that basically counts or jumps through a set of different states or counts values, and if the state is correct, it would generate a signal that enables a particular computation to happen. Okay. Now, this is probably going too fast at this point, but it's something that we will be coming across later. What is important now is that the notion of a finite state machine is important for you to know. How exactly finite state machines are implemented, how can I implement them optimally using JK flip-flops or D flip-flops and so on, is not essential, right, because what we will be doing in practice is we will actually be writing Verilog or HDL programs for these and directly converting these into hardware descriptions there will be computer aided design tools that will take care of all the optimizations that we need.